Okay, so this is section 5.6, day 2. We're talking about simplifying negative exponent, or negative square roots, sorry about that, and quadratics with negative discriminants. So before we begin, we had a couple warm-up problems here. On the left-hand side of our Cornell notes, I asked everyone to simplify negative 4 plus 4i divided by 2 as problem number 1, and then number 2 was 6 plus 4i divided by 2. So I'll pause. Okay, so here's what you should have got for the warm-up, right? We had negative 4 plus 4i divided by 2. And some people know about this thing called the v-check, right? Where you can, if you have a fraction and negative 4 can divide 2 and 4 can divide 2, it makes a v, then you know you can keep going. So what I did was I factored out a negative 4 from the numerator, which gave me negative 4 times 1 plus I, and then all divided by 2. And negative 4 divided by 2 simplifies to a negative 2, so I put a negative there. So then I get negative 2 times 1 plus I, and then I distribute for a final answer of negative 2 minus 2i. So this is the final answer right down here. And then for this one, right, 6 plus 4i divided by 2, well, I could do the v-check again. 6 can divide 2, 4 can divide 2, so I know I can keep going. So that means I factored out a 2 from the top, and that left me with 3 plus 4i, all divided by 2. My 2's cancel out, leave me with an answer of 3 plus 4i. So that's how you simplify those fractions. We're going to do that in the lesson today. Okay, so first we're going to talk about the complex conjugate theorem. And it says this: so let z be any complex number such as like a plus bi. Then z with a line over it is called the complex conjugate, and it's just a minus bi. That's called the conjugate. And we spoke a little bit about that on I think Friday it was. So if you take z and then you multiply it by z conjugate, algebraically you'd get a plus bi multiplied by a minus bi, right? So that's z, and then that's z conjugate. Well, it turns out when you multiply those things together, all you really end up with is a squared plus b squared. So that's a little theorem there that can help us out. Let me give you an example of that, right? So if I had an example of 2 plus 3i, okay, and that's z. If I multiply that by the conjugate, 2 minus 3i, that's z bar, it's just going to be the same thing as a squared plus b squared, where 2 represents the a and 3 represents the b. So for my answer, all I get is 2 squared plus 3 squared, which is, of course, just 4 plus 9, so it's the answer of 13. So 2 plus 3i times 2 minus 3i is the same thing as 13, because this is 4 plus 9. That's how I got that. Okay, so that's the first thing we did, the complex conjugate theorem. Then we spoke about how to simplify negative square roots, and this is just like simplifying a regular square root, except there's a negative involved, right? So before we'd say, well, we can't go any further because we can't take the square root of a negative number because that's not a real number. But now we have this imaginary number system, so here's what we can do. We can say this is the square root of 9 times negative 1, right? Because negative 9 is the same thing as 9 times negative 1. Well, I'm allowed to split up the square roots into the square root of 9 times the square root of negative 1. That doesn't look like a negative 1, though. Here we go, negative 1. So the square root of 9, this is a real number. I can easily take care of that. And the square root of negative 1 is defined to be this imaginary unit. So then I have the principal square root of the square root of 9 is 3, and then the square root of negative 1 is I. So the principal square root of the square root of negative 9 is 3i. So same thing works over here, right? This can be broken up into the square root of 4 times negative 1, which is the same thing as square root of 4 times the square root of negative 1, which is 2i. So the principal square root is 2i. The book talks about the principal square root only being the positive one. 13 is a prime number. I can't do anything with that, but I can break this up in the square root of 13 times negative 1, all underneath the square root, which is the square root of 13 times the square root of negative 1, which is just square root of 13i for an answer. And then square root of 12, square root of negative 12 can be broken up into the square root of 4 times the square root of 3 times the square root of negative 1. If I skip that step there, here, I'll show you what I did. I just did 4 times 3 times negative 1, and then broke them up into square roots. So now the square root of 4 is 2. Square root of 3 is just square root of 3, and square root of -1 is I, so the principal square root is 2 rad 3I. Okay, so there's simplifying negative square roots. Now that we have all this underneath our belt, let's try and solve an actual quadratic. So first we have three choices here, right? We can solve by factoring quadratic equation or completing the square. And in this section, we're going to focus on the quadratic equation. We can't factor anyways because 13 is a prime number, and I can't add or subtract and make a -6 out of that. So first, get A. A is 1, B is -6, and C is 13. Then check the discriminant, b squared minus 4ac. Okay, so that's going to give me -6 squared minus 4 times 1 times 13. -6 squared is a positive 36. Take away 4 times 15 is 52. So I have a -16 for my discriminant. So here's what that means. That means I'm going to have two complex solutions in the form of, a plus or minus bi, and they will be conjugates of each other. That's an important part. So now we know what to do with this negative discriminant. It used to be like, well, there's no real solution, but now we can figure out that we can keep going with this. So here we go. X is going to be -b, which is going to be 6, plus or minus the square root of -16, all of my work in there, divided by 2 times a. 2 times 1 is just still 2. So breaking down that negative square root gives me 6 plus or minus 4i divided by 2. Doing a v-check now, 6 can divide 2, 4 can divide 2. So that can give me, I'll take out a 2 from the top, 3 plus or minus 2i, all divided by 2. My 2's can then cancel, leave me with 3 plus or minus 2i for my answer. And notice that those are conjugates of each other, right? One is 3 plus 2i, and the other is 3 minus 2i, just like the theorem said that was going to happen. Okay, so there's your answer, 3 plus or minus 2i. Of course, that's a complex number. It's not a real number, but now we know how to solve quadratics with negative discriminants. Okay, I was going to have you guys try it on your own. Okay, here's what I got, right? First, I figured out A was 1, B was 4, and C was 8. I checked the discriminant, and I got a -16, again, which told me that there's going to be two complex conjugate solutions. Plugged it into my quadratic formula, simplified my negative square root, factored out a 2, and got the answer of -2 plus or minus 2i. So hopefully you got that as well. All right, there you go.